Multivariable Calculus, Section 14.3. Fundamental Theorem and Independence of Path. The fundamental theorem of calculus. In single variable calculus, we have the integral from a to b of g prime of x dx equaling g of b minus g of a. The fundamental theorem for line integrals goes like this. Let f be a function of 2 or 3 variables and c be a smooth curve parameterized by the vector-valued function r of t for t between a and b. If f is continuously differentiable at each point on c, then the line integral of the gradient vector of f dotted with dr is equal to f of r of b minus f of r of a. If we name the endpoints of the C curve A and B, then we can merely write the answer to the integral as f of b minus f of a, and so it resembles the fundamental theorem. Now notice that the gradient vector is the vector of partial derivatives for f, and so therein lies the relationship then. F is like an antiderivative for the gradient vector. Now recall that this integral computes the work done by the gradient vector field in moving a particle along C from A to B. Now we're going to do a proof of this fundamental theorem because it's a fairly simple proof. So here's the proof of the line integral gradient vector dotted with the change in vector r equal to f of r of b minus f of r of a. So we start off with the line integral and delineate it with what it represents. The gradient vector of f is the vector with the partial derivatives of f with respect to x, y, and z. If we're doing it for 3 dimensions, the proof for 2 dimensions would be exactly the same. And that's dotted with the change along vector r, which would be dx, dy, dz. Change in x, change in y, change in z. And so if we dot those together, we get this result. And now we need to change to t, and so we're going to multiply by dt over dt. And what we're going to do is we're going to bring the denominator dt into the parentheses. And so we get the partial derivative of f with respect to x times dx dt plus the partial derivative of f with respect to y times dy dt plus the partial derivative of f with respect to z times dz dt, all integrated with respect to t. Now that integrand should remind you of something, and we're going to define g of t to be f of r of t, which would be the set of parametric functions for each of x, y, and z, and then operate on those by f. And then from section 12.7, that integrand above, by definition then, is the derivative of g. And so if we're integrating, now we've got a single variable integral of a derivative from a to b, so naturally the antiderivative evaluated to be an a is the result, and because g was defined as f of r, then we end up with the result we wanted to show. Quod erat demonstratum. Alright, so moving on, we need to look at some more terms and what they mean. So from Wikipedia, a conservative force is a force with the property that the work done in moving a particle between 2 points is independent of the path taken. Gravity is an example of a conservative force, while friction is an example of a non-conservative force. And so we've been looking at an integral that computes the work done by a force, and now we're going to look at when in fact the curve C is not important, and that no matter what curve we followed, the same work would be done in moving from point A to point B. So for example, let's say we have an apple that drops straight down, or maybe we have an apple that drops sideways. Whether falling straight down from the top of a building or diagonally, say from a moving airplane, gravity does the same amount of work per vertical distance. That's why it's a conservative force. Independence of path. What exactly does that mean? Well, let's say we have a little fella and he's carrying a heavy load of recycling materials, and he walks along a particular path from point A to point B. And then let's say he takes the same amount of materials from point A to point B, but takes a longer path. Well, in this case, is he going to do the same amount of work? No, because the longer the path he takes, the longer he's carrying the heavy load and the more work he's going to do. So this is an example that is not independent of path. If the same amount of work is done going from point A to point B, regardless of the curve followed, then the integral of the force is called independent of path. Line integrals of conservative vector fields are independent of path. Now this little guy then is not working in a conservative vector field. Now before we continue, we have to talk about types of paths and types of curves. So here we have a simple curve that is not closed. It doesn't cross itself, but there are two separate endpoints. This curve is simple and closed. Simple in that it doesn't cross itself, and closed in that it has no endpoints. It just keeps going round and round. This one is not simple because it crosses itself, and it's not closed because there are two endpoints. And finally, this curve is not simple, but it is closed. It's not simple because it crosses itself. So the line integral f dotted with dr is independent of path if and only if the line integral equals 0 for every closed curve C. Well, how can this be? How can the work be 0? Well, it's because work done to the right and work done upward is considered positive work, and work done to the left and work done downward is considered negative. And so if they cancel out, then that means it doesn't matter for every closed curve, then that means it doesn't matter which closed curve you're going, you're doing the same amount of work one way as you are the other way. Now this isn't very useful because we can't possibly examine every single closed curve to determine whether we have independence of path or not. So there's a better way. So here's the theorem. The line integral f dot t ds, which is equivalent to the line integral f dot dr, as we've seen in a previous section, of a continuous vector field f is independent of path in a region D if and only if the force is a gradient vector for some function f on D. And so if the force is a gradient vector, then we know we have independence of path, and the gradient vector is a conservative force. Now here's some more definitions. If f in fact is a gradient vector for some function f on a region D, then f is called a potential function for f, and f is called a conservative field. This is the key to all the problems in the text. All the other stuff is just interesting, but this is what we use to determine whether we have a conservative field that's independent of path or not. We have to look at the force function in the line integral and decide, is this in fact a gradient vector function? And if it is, we are going to be able to find the antiderivative, so to speak, of that gradient vector function, which will be f. In numbers 1 through 16, determine if the vector field capital F is conservative. If capital F is conservative, find a potential function little f. Now we're going to do this all at once. We're going to examine big F and try to determine if in fact there exists a little f. Alright, so here's number 2. And if in fact big F is conservative, then the gradient of little f is equal to big F. Now the gradient, you'll remember, the first component is the partial derivative with respect to x. So going backwards, that means a possible potential function would be 2x squared. That's what happens to 4x when you integrate it with respect to x. And then minus y is treated as though it were constant, so you get minus y times x. And then the tricky part is there could have been a function purely in terms of y that would have gone to 0 when you took the derivative, the partial derivative with respect to x. Now then the second component is a partial derivative with respect to y. So we integrate, we go backwards using y as our variable and x as a constant. So 6y becomes 3y squared and minus x becomes minus xy. And then of course there could have been a function purely in terms of x, a term purely in terms of x that went to 0. Now, does this work? Well, the part that has both x and y in it, the term with x and y in it, matches. And our c1y could certainly be 3y squared. And then 2x squared could be our c2x. So we have a match. And so if we combine these two answers, we do get a potential function. And therefore f is a conservative vector field, and the potential function, putting those together, is 2x squared plus 3y squared minus xy plus possibly a constant, because c1 and c2 could have had a constant involved. Number 6. Big F is this function, a vector valued function, and if in fact it's conservative, then the gradient vector is equal to big F. And so again, starting with our first component, we go backwards, treating x as a variable and y as a constant, and we get 4/3 x cubed times y minus 5x y to the 4th, and then possibly a function in terms of y that went to 0, a term in terms of y that went to 0. And then the second component, using x as though it were constant and y as the variable, going backwards from the partial derivative with respect to y, we get x cubed times y minus 5x y to the 4th plus possibly a function or a term in terms of x. Now we have a problem here because the term that involves both the x and y does not match. Therefore, no potential function f of xy exists for this vector field. Hence, f is not a conservative vector field. Number 10. F is equal to x plus arctan yi plus x plus y over 1 plus y squared j. If f is conservative again, then we have a gradient vector equal to f. And so that's what we have to work with. So again, the first component, we go backwards with x as our variable, and we get 1/2 x squared plus x times arctan y, because arctan y is just treated as a constant, plus possibly a function in y that went to 0. And then going backwards from the second component is a little trickier. We have to split that into two fractions. And the first one is easy because x is just a constant, so that would just be x times arctan of y. Second one, we could do a u sub. You could possibly do that in your head, I'm not sure. But if we let u equal 1 plus y squared, then du is 2y, and so all we need is a half to take care of that. And so our possible potential function from the second component is x arctan y plus a half the natural log of 1 plus y squared plus possibly a function in terms of x. So our x and y term matches again, and we have a match for c1y and we have a match for c2x. So therefore, since everything matches, f is a conservative vector field, and our potential function is x arctangent y plus the half x squared plus the half log 1 plus y squared, and then possibly a constant that went to 0 both times. Number 14. Here's our vector field, and again, if it's conservative, then it's equivalent to the gradient vector for f. So working with our first component and treating x as a variable and y as a constant, we get e to the x sine y plus x tan y plus a term in terms of y only. And then for the second component, treating y as a variable, we get e to the x sine y plus x tangent y plus possibly a function in terms, or a term in terms of x only. Now you'll notice that in the first calculation there is nothing in terms of x only, and in the second calculation there's nothing in terms of y only, so that must not have occurred. However, both terms in terms of x and y do match, and therefore we have a match, and f is conservative. And the potential function is a combination of those two terms. Plus, of course, there could always be a constant that went to 0 both times. Number 20. Find the potential function for f, big F, given this way, by converting to parametric form and integrating the integral f dot t ds. Well, this is like the hard way to do it, so at the end we'll check it doing the easy way, but let's do it just so we get practice with parametric form. Recall that from a previous lesson, this line integral is equivalent to p dx plus q dy plus r dz, and in our case we don't have a third term, so we're only using 2 dimensions. So, following the example 4 in the Edwards and Penney textbook, we set x equal to x1t and y equal to y1t for t going from 0 to 1, because we want to be able to do this for any curve, and so the endpoints would be determined by x1 and y1. And so now we just have p, which is the first component in front of I dx, plus the second component, the one in front of j, dy, as our integrand. But we can't integrate when we're mixing it up this way, so we have to, for this particular form, we have to change to parametric. So now we're going to substitute for x and y, and t then goes from 0 to 1. And remember, x1 and y1 are like your a and b, they're just numbers. Okay, so now we have something that looks pretty horrible, but we can simplify that by collecting like terms and factoring out the dt. And now we've got something that we can work with. We're going to take the antiderivative with respect to t. So we get x1t, and then notice that we have a 2t in front of the exponential term, and so that's the baby for t squared. And so the 2t goes away. Oh, and also you've got x1, y1 as the coefficient of t squared. So the baby for x1, y1, t squared is your 2x1, y1, t, and so that just goes away. And then in the last term, 2t, the antiderivative of 2t is t squared, and we keep the coefficient. And that's going to be evaluated from 0 to 1. So substituting 1 for t, we get x1 plus e to the x1 y1 plus y1 squared, and then substituting 0, we get 0 plus 1 plus 0. Now for our potential function, though, the constant can be anything. So substituting x and y, our potential function is x plus e to the xy plus y squared plus k. And we could have gotten that a lot more simply doing it the way we did the other problems without converting to t. But it's the idea here that counts, and to show you that it can be done. In number 21 through 24, show that the given line integral is independent of path and then evaluate it. So for number 22, we are going from 0, 0 to 1, 1, and this is p dx plus q dy, and so if in fact it's independent of path, these are the components of a gradient vector, which are the partial derivatives with respect to x and then with respect to y for the second component. So for the first component, we work backwards using x as our variable, and we get x squared minus 3xy plus possibly a function of y alone. Second component, we work backwards with y as our variable, and we get y squared minus 3xy plus possibly a function in terms of x. Now we do have a match for our xy term, and then the individual terms with x and y are pretty obviously x squared and y squared. So we do have a potential function, and therefore this line integral is independent of path. Now we don't have to switch to t because our potential function is an antiderivative. And so all we have to do then is evaluate the antiderivative from 0, 0 to 1, 1, and we don't need the plus k because it drops out. So we plug 1 and 1 in for x and y, and then we plug 0 in for both x and y, and get our answer of -1. Number 24, similar. We're going from 0, 0 to 2 pi, 2 comma pi. And again, if first we show that it's independent of path, because see, then we don't have to worry about what c is, we just plug the endpoints into the antiderivative. So going backwards with respect to x, we get x cosine y. Going backwards with respect to y, we get x cosine y plus a function of x. And notice that the reason the negative sign's gone there is because the antiderivative of sine is negative cosine, so the negatives cancel. So we have a match, and we don't have any terms in just x or y, and so our potential function is just x cosine y plus possibly a constant. And that means we can evaluate this line integral using that as our antiderivative. So we plug 2 in for x and pi in for y, and then we plug 0 in for both x and y, and get an answer of -2. Number 28, find the potential function for the vector field given here. Now the difference now is that we have a third component, so it gets a little bit more complicated, but not much. So if in fact there's a potential function for this vector field, then that means this is a gradient vector. And so the first component again is the partial derivative of f with respect to x. So we go backwards treating x as the variable, and we get x squared minus xy minus xe plus, now this time if there were any terms in terms of just y or just z or both y and z but no x's, then they would have gone to 0. So we could have several terms for c1. The middle component is the partial derivative of f with respect to y, so we treat y as our variable and we get y squared minus xy, and then there could be terms with just x's and z's in them, x and z or x or z. And then finally the last component we treat z as our variable because this is the partial derivative of f with respect to z, and we get z squared minus xz plus possibly terms with x's and y's in them. So now we have to put these three together. Do we have matches? Well, I see that the negative xy matches, but is that all that could be in the C3? Are there any other terms with just x and or y in them? And yes, there are a couple other ones. So we have to include those, and there's no contradiction yet. And they told us there would be one, so we don't have to worry too much. And then what else have we got? Well, we've got terms in just x and z. Well, we already have the x squared, and now we need the minus xz. And then is there anything else in terms of x and z? Yes, there's a z squared there. And so that takes care of our possible terms that only have y's and z's in them. Or does it? Are we done here? I think we are. We've got everything marked out. And of course there could be plus a constant. And I leave you now with an interesting little movie. We have 1 dimension, 2 dimensions, 3 dimensions, and then 4 dimensions. And these are all sort of equivalent to the idea of a cube in 3 dimensions. Line segment, square, cube, hypercube. Line segment, square, cube, hypercube. Enjoy your problems in section 14.3.